Welcome to WikiPodcast. Today we're taking a deep dive into something absolutely fundamental to our modern world, yet often invisible. How electric current flows and powers everything around us. This is a core piece of physics, specifically within electricity and magnetism. Think about plugging in your phone, flipping a light switch, or even the signal zipping around in your brain. It's all about electric charge on the move. This is our Electric Circuits and Current episode.
Exactly. And our mission today is really to unpack the core concepts of electric current. We'll define what it is, explore the fascinating ways it behaves in different materials, understand key relationships like Ohm's law, and maybe uncover some surprising places electric current shows up. It's about getting a handle on these unseen forces that, well, drive so much of our lives.
Absolutely. Yeah. So we're going to explore everything from like the tiniest particles moving in a wire to those massive power lines you see spanning continents. We're going to look at what current is, how we describe it, and why grasping this fundamental flow of charge is just so crucial for making sense of our electric world. So let's just start at the beginning. What is electric current at its most basic level?
Fundamentally, electric current is the flow of electric charge. Simple as that. It's defined very precisely as the net rate at which electric charge passes through a specific point or, say, a surface.
Okay, so it's about charge moving. What kind of charged particles are actually doing the moving? Because I know it's not always just electrons, right?
That's exactly it. The specific particles carrying the charge, we call them charge carriers, they depend entirely on the material or the medium. In your standard metal wires, you're absolutely right. It's primarily electrons doing the work.
No.
But if you look at semiconductors, like in computer chips, the carriers can be electrons, or these things called holes, which are basically missing electrons that act like positive charges. Holes.
Okay.
And then in liquids, like the electrolyte inside a battery, the carriers are ions, so positively or negatively charged atoms or molecules moving around. And in gases or plasma, you can have both ions and free electrons flowing.
Got it. So it's any moving charge. And what kind of charge carrier it is depends on what it's moving through. Makes sense. And how do we measure this flow? What unit do we use?
In the standard SI system, we measure electric current in amperes, or often just amps. The symbol is A.
Amps.
Right. And 1 ampere is defined as 1 coulomb of charge passing a point every single second. It's actually a fundamental unit in physics. You'll also sometimes hear people refer to the current itself as amperage.
And I've often seen the symbol I use for current in formulas. Where does that come from? Is it just intensity?
Yeah, pretty much. That symbol I actually comes from the French phrase intensité de courant, meaning current intensity. It was popularized by André-Marie Ampère way back in the 1820s when he was figuring out his force law for current-carrying wires. The unit, the ampere, was later named in his honor, and the symbol I just stuck around.
Okay, that makes sense. Now, here's something that kind of tripped me up initially when I was first learning this whole idea of conventional current direction.
Yeah.
In metal wires, we just said the carriers are negative electrons, right? And they typically flow from the negative terminal of a battery towards the positive. But the conventional current direction is often drawn the other way. What's up with that?
That's a really important point. And yes, it is a bit counterintuitive. The convention was established historically, well before we fully understood that the charge carriers in many common materials, like metals, were actually negative electrons. They just sort of arbitrarily defined the direction of current as the direction that positive charges would flow.
So wait, if negative electrons flow from negative to positive, and positive charges would flow from positive to negative, then in a typical wire circuit, the conventional current flows in the opposite direction of the actual electron movement.
Precisely. In most wire circuits, the conventional current direction runs opposite to the physical electron flow. It's just a standard, a convention we all agree on for circuit diagrams and analysis. It makes the math consistent.
Okay.
So when you're analyzing a circuit, you assign a reference direction for the current. Usually you draw an arrow. If your calculations then give you a negative value for the current in that direction.
It just means it's actually flowing the other way.
Exactly. It simply means the actual conventional current is flowing the other way compared to the arrow you drew. It's just a tool for consistency, not necessarily a literal picture of the particle movement in every case.
All right. That clarifies things. Phew. Now let's get to one of the most famous relationships in electricity, Ohm's law. What does that tell us about current?
Right, Ohm's law. It describes a really fundamental linear relationship between the current Mn flowing through many types of conductors, the potential difference, or voltage V, across that conductor, and the conductor's resistance.
And the simple formula everyone knows is I equals VR. So if you increase the voltage across something with a fixed resistance, you get more current flowing. Simple enough. And if you increase the resistance, maybe use a different material while keeping the voltage the same, you get less current.
Exactly.
And for materials that obey Ohm's law, that resistance R is constant, right? It doesn't matter how much voltage you apply or how much current flows, the resistance stays the same.
That's the key for ohmic materials, yes. It's a cornerstone for analyzing many, many simple circuits. Now, when we talk about current flowing, we often hear about two main types, AC and DC. What's the difference there?
Yeah, AC/DC. Let's start with DC, direct current. That sounds simpler.
It is, generally. With DC, the charge carriers flow in one direction only, consistently. Think of a battery powering a flashlight or the output from a solar panel. The current flows steadily from the positive terminal to the negative terminal, using that conventional direction we just talked about.
Yeah.
Historically, it was sometimes called galvanic current.
Okay. Steady, one-way flow, and then there's AC, alternating current.
Right. This is where things get a bit more dynamic. With AC, the direction of the charge movement periodically reverses. Back and forth, back and forth. This is the type of power that's delivered to most homes and businesses from the power grid. It typically alternates in a sine wave pattern.
Right, that back and forth sine wave. AC is also used extensively in carrying information, isn't it? Like audio signals or radio waves.
Absolutely. While power transmission is, the most common association for most people, alternating current is essential for carrying signals. By varying the amplitude or the frequency of that alternating current, you can encode information onto it. That's the basis of radio, television, and tons of communication technologies.
And just quickly, speaking of historical drama, the debate over whether to use AC or DC for widespread power distribution was famously a big deal, right? The War of the Currents.
Oh, absolutely. That's a whole deep dive in itself. Edison versus Tesla and Westinghouse. Fascinating stuff.
Okay, so current is moving charge, measured in amps, related to voltage and resistance by Ohm's law, and comes in DC and AC flavors. Where does this electric current actually show up in the world? Beyond our power outlets and gadgets? Are there, surprising places?
Oh, definitely. Electric current isn't just a man-made phenomenon stuck in wires. It occurs naturally in quite spectacular ways. Lightning, obviously, is a massive transient electric current between the clouds and the ground.
Huge current.
Static discharge when you touch a doorknob after walking on carpet, that's tiny, quick current. Even phenomena like the solar wind interacting with Earth's magnetic field, which causes the beautiful auroras that involves complex electric currents flowing in space and our upper atmosphere.
Wow. And on the man-made side, beyond the obvious power lines and the circuits inside our phones.
Yeah.
What else?
Well, you find it in some interesting effects. Changing magnetic fields can induce currents inside conductors. These are called eddy currents. They can be useful or sometimes a source of energy loss. And the currents flowing on the surfaces of conductors when they interact with electromagnetic waves are fundamental to how antennas transmit and receive radio signals.
And you mentioned brains earlier. That's current too.
Yes. Perhaps one of the most surprising places for many is within our own bodies. The signals transmitted along our nerves and firing within our brains involve the flow of ions, essentially tiny electric currents. That's how we think, feel, perceive, and move. It's bioelectricity.
Wow, okay. From lightning bolts to brainwaves, it really is everywhere. You mentioned measuring current earlier with an ammeter. How does that actually work, and are there other ways?
Right, a basic ammeter. It's designed to be placed in series with the circuit element you want to measure the current through.
In series, meaning the current has to flow through the meter itself.
Exactly. The current goes into the meter and comes out the other side. Because of that, ammeters are designed to have very, very low resistance, so they don't significantly affect the circuit they're trying to measure. Historically, galvanometers were used. They detect current by its magnetic effect, but they also generally require being placed in series.
But what if you don't want to break the circuit open? I mean, cutting wires isn't always practical. Are there methods that can detect current without, physically inserting a device into the path?
Yes, absolutely. And many modern methods take advantage of that fundamental effect we touched upon earlier. Electric current always creates a magnetic field around it, so you can measure the strength of that magnetic field to figure out the current flowing without ever breaking the circuit.
Ah, that's clever. So like those clamp meters electricians use, they just clip it around a wire.
Exactly. A current clamp, or clamp meter, wraps around the wire and measures the magnetic field produced by the current flowing through it. This lets you measure the current, usually AC, without direct electrical contact. Other methods include using special, very low-value resistors called shunt resistors. Though these do technically go in series, they're designed to divert only a tiny measurable voltage drop. There are also Hall effect sensors and other magnetic field sensors. Transformers can also be used to measure AC current inductively.
It's fascinating how that magnetic field effect is so fundamental it allows both measurement and has other really significant consequences, right? You mentioned motors earlier.
It really does. That intimate link between electricity and magnetism is one of the most powerful concepts in physics. Maxwell's equations territory. Electric currents don't just create magnetic fields. That interaction is the basis for electric motors, where a current flowing in a magnetic field experiences a force, producing rotation and motion, and of course, electromagnets.
Like wrapping wire around a nail, connecting it to a battery, and picking up paper clips.
Precisely. Run current through that coil of wire, it becomes a magnet. Turn the current off, the magnetism pretty much disappears. That direct, controllable relationship is incredibly useful in relays, speakers, MRI machines, countless things.
And the reverse is also true, and just as important, you said, changing magnetic fields can create electric currents,
Absolutely. That's electromagnetic induction discovered by Faraday.
which is how generators work, isn't it?
Spot on. If you move a conductor through a magnetic field, or maybe easier, you vary the magnetic field near a conductor, it induces an electromotive force, or EMF, basically a voltage, across the conductor. If there's a closed path, a circuit, that EMF will drive a current. This is exactly how electric generators produce electricity. They use mechanical energy from wind, water, steam to spin coils of wire within magnetic fields or spin magnets near coils, inducing current.
So current causes magnetism, and changing magnetism causes current. A beautiful symmetry. What other effects does current produce?
Another major unavoidable effect is heating.
Yes, things get warm.
As current flows through any material that has some electrical resistance, which is pretty much everything except superconductors, it converts electrical energy into heat. We call this Joule heating or ohmic heating.
Named after James Prescott Joule, who studied this carefully. And there's a formula for that too, right? Something about current squared.
Yes, the power dissipated as heat, P, is proportional to the square of the current multiplied by the resistance R. So P is proportional to IRR, double the current, and you get 4 times the heat, assuming resistance stays constant.
Right. And this heating is exactly why the filament in an old incandescent light bulb glows hot enough to emit light. It's also why transmission lines have losses, and why your computer's CPU needs a fan.
Exactly. And it's also, as we sort of mentioned earlier, the origin of those electromagnetic waves, like radio waves. When the current isn't steady DC, but is time varying, especially at high frequencies, the accelerating charges radiate energy.
Okay, now we touched on it briefly, but let's take a closer look at how electric current actually flows differently in various materials. We said the charge carriers vary, but what does that look like on a microscopic level? It sounds complex.
It is, yeah. The microscopic mechanism differs quite a bit, and it's pretty interesting. Let's start with metals, the most common conductor. In metals, you have this sea of electrons. The outermost electrons aren't tightly bound to individual atoms. They're sort of free to roam throughout the metal lattice.
Okay, C electrons.
When you apply a voltage, like from a battery, it creates an electric field inside the metal. Now, these electrons don't just zip straight through from one end to the other. They're constantly bouncing around randomly at high speeds due to thermal energy colliding with the atoms in the lattice structure. The electric field just provides a tiny, tiny nudge, a bias to this random motion. It causes them to drift, on average, very slowly in the direction opposite to the electric field, since electrons are negative. This slow average movement is the net current.
And for a steady current flow, we could define the current I as the total amount of charge Q passing a point over a given time t. So I equals QT.
Right, or more generally, especially if the current is changing, it's the weight of change of charge over time, the derivative dq dt.
Okay, so that's metals drifting electrons in a sea. Now contrast that with, say, electrolytes, like in a battery.
Right. In electrolytes, it's not electrons freely moving through the structure. It's ions, entire charged atoms or molecules physically moving through the liquid or gel. You might have positive ions drifting one way towards the negative electrode and negative ions drifting the other way towards the positive electrode. The total current is the sum of the charge carried by both types of ions moving in effectively opposite directions relative to each other, but contributing additively to the external circuit current.
Mm-hmm.
And it's not just liquids. Even ice under certain conditions and some solid electrolytes used in modern batteries can conduct electricity using moving protons, which are positive hydrogen ions.
Protons moving, fascinating. And gases or plasmas, you said they're normally insulators?
Yes, normally gases don't conduct well. But if you apply a strong enough electric field, you can rip electrons off the gas atoms or molecules, ionizing them and creating a plasma. Think lightning again, or a fluorescent tube. In a plasma, you have lots of free electrons and positive ions mixed together. Both can move and carry current. Because the electrons are much, much lighter than the ions, they move much faster in response to the electric field and usually carry the bulk of the current.
Okay. What about a vacuum? Can current flow through nothing?
A perfect vacuum is an excellent insulator, yes. There are no charge carriers inherently present, but you can get current to flow across a vacuum if you inject charge carriers into it. For instance, you can heat a metal surface until electrons boil off. That's thermionic emission.
Like in old vacuum tubes.
Exactly like in old vacuum tubes. Or you can apply a very strong electric field to pull electrons out of a metal surface field emission. Once the charges are in the vacuum, they can be accelerated across it by an electric field, creating a current.
Right. And then there are semiconductors. They're kind of the magic materials for all modern electronics, but they're not quite conductors or insulators. How does current work there?
Semiconductors like silicon are fascinating because their conductivity is somewhere in between conductors and insulators, and crucially, it can be controlled. As we mentioned, current can be carried not just by electrons that get enough energy to break free into what's called the conduction band,
Conduction bands. Look it
but
up.
also by the holes left behind in the valence band where those electrons used to be. Applying a voltage can cause electrons to jump into nearby holes, effectively making the hole appear to move in the opposite direction, like a positive charge carrier. The whole concept of energy bands and the energy gap between the valence and conduction bands is critical to understanding how semiconductors work and how we can dope them with impurities to precisely control their conductivity.
That sounds like a whole topic in itself, too. And finally, superconductors. Zero resistance sounds like it breaks the rules.
It almost feels like it. Below a certain critical temperature, which is often very low, these special materials enter a quantum mechanical state. In this state, electric current can flow indefinitely without any electrical resistance, meaning no energy loss to heat zero joule heating. The electrons effectively form pairs, Cooper pairs, and move collectively in a highly ordered way that avoids the scattering and collisions that cause resistance in normal metals. It's purely a quantum phenomenon.
It's just incredible how different the actual mechanisms are, from drifting electrons to moving ions to quantum pairs, even though we describe the overall flow with the same unit, the ampere. Speaking of the flow, we mentioned the average drift speed of electrons in a wire earlier. Remind me how slow that was again. It seemed unbelievable.
It really is surprisingly slow.
Yeah.
For a common copper wire carrying a typical household current, say 1 amp through a wire a couple of millimeters thick, the average drift speed of the individual electrons might only be about a millimeter per second, or even less.
A millimeter per second. That feels completely wrong. If electrons are drifting that slowly, how on earth does a light turn on the instant you flip a switch, even if the power station is miles away?
This is where the really interesting insight lies, and it's often misunderstood. It's a great question. The speed at which the individual charge carriers drift along the wire is indeed very, very slow, like snail's pace, almost. But the speed at which the electrical energy or the signal propagates through the circuit is vastly, vastly faster. It's practically instantaneous on human scales.
So it's not like a chain reaction where the first electron pushed at the switch has to travel all the way to the light bulb.
Exactly. It's not like that at all. Think of it like the analogy our sources sometimes use. Imagine a pipe completely full of water.
Okay, full pipe.
When you turn on the tap at one end, forcing a little more water in, water starts coming out the other end almost instantly, right?
Yeah, pretty much straight away.
But any individual water molecule you pushed in at the start might take a very long time to actually travel the whole length of the pipe.
Ah, I see. So the pressure wave travels fast, but the water itself moves slowly.
Precisely. It's similar with electricity. The electric field, the electromagnetic wave carrying the energy and the turn-on signal, propagates along the wire extremely fast, close to the speed of light in the surrounding medium. This field gets all the electrons along the entire length of the wire drifting almost simultaneously, though still slowly. So electrons near the light bulb start moving through the filament almost instantly when the switch is flipped, even though the electrons from the switch haven't gotten anywhere near there yet.
That really changes how you visualize it. The electrons are the medium, the necessary carriers, but they aren't the ones delivering the punch of energy instantly across the circuit. It's the electromagnetic wave propagating through and around the wire.
Exactly. The energy is actually transferred primarily through the electromagnetic field surrounding the wires, guided by the wires themselves. Understanding electric current isn't just about IVR, it's about appreciating these different behaviors, the surprising difference between drift speed and signal speed, and that fundamental link to magnetism and energy transfer.
So just to sort of wrap it all up then, we've seen that electric current is this essential flow of charge. It's described by relatively simple laws like Ohm's law for many materials, but the way it actually happens, the charge carriers and their motion, behaves very differently depending on the material, from metals to electrolytes, semiconductors, plasmas, even superconductors.
Mm-hmm.
And this flow is responsible for generating magnetic fields, creating heat, producing light, carrying signals, and ultimately powering our entire modern world through this incredibly rapid propagation of energy via electromagnetic fields.
Absolutely. Understanding these fundamental ideas hopefully gives you a much clearer picture of the unseen forces at play in everything around you. From natural wonders like lightning and auroras to the intricate technology you use every day, it's a truly foundational concept in physics with incredibly broad and tangible applications.
Okay, here's something to think about then. Consider this. Knowing that the electrons in a wire might only be drifting a few millimeters per second, but the electrical signal, the light turning on, happens almost instantly. What does that really tell you about how energy is transferred in an electrical circuit? Where is the energy actually flowing?
Oh,
Thanks for listening. Write us your opinion in the comments on how this deep dive changed your perspective on simply flipping a light switch. Subscribe to the channel to help more listeners reach our episodes. Thank you. Have an amazing day.